So last time we were talking about, like I was mentioning, stoichiometry, and we started talking about, I think, limiting reagents. Remember that limiting reagents, sometimes called limiting reactants as well, is the idea that when you have a chemical reaction that's taking place, there's usually one reactant that really does sort of run out first, if you will. So there's usually a reagent that gets used up first. And when we have that reagent that gets used up first, that is what is referred to as the limiting reagent. We obviously also then have sort of a reagent that we have plenty of and we really don't run out. And that is what is known as the excess reagent. And the importance of the limiting reagent, as we talked about last time, is it is really the one that gets used up first is really the one that determines how much product you can make. It's really that guy there that's going to determine really how much product you can make. And it's just a very simple idea of, again, I think maybe I use this example. If you take A plus B and you want to make A, B together, if we said at some point here we ran out of A and we used it all up, we clearly at that point is when we would stop making products. So we always want to sort of use the limiting reagent to determine, how much product that we produce. When we do a calculation and figure out really how much products produced from a reaction, that is what is sometimes referred to as our theoretical yield. And we talked about some different yields last time as well, but our theoretical yield is really your maximum amount of product that you would make based off of the equation, based off of how much you're starting with, and really based off of the idea that everything went perfect in that reaction. You didn't spill anything, didn't drop anything, there was no side reactions. That reaction was like 100% complete, everything went perfectly. That would be your maximum sort of yield. In reality, that usually doesn't obviously happen, even in sort of the best ideal circumstances, that usually doesn't happen, and we usually get what is known as the actual yield. And much like the name implies, that's actually how much you produce as a result of the reaction. And the relationship between theoretical and actual yield gives us sort of a third yield, if you will, and that's sort of a yield we oftentimes think about when we do perform reactions and we try to figure out, how well did we sort of do this reaction. That's what's sometimes referred to as percent yield. And when we do the percent yield, it's your actual yield divided by your theoretical yield times 100%. And again, usually when we do percent yield, we're looking for something in terms of a large number. In a lot of cases, we don't usually get 100% yield, but nearing 100% yield is extremely good. Above 90 is really good and stuff like that. We also talked about the idea that you could, in theory, get over 100% yield. And in theory, what that really means is you probably screwed up somewhere. So, as we talked about last time, it's a very common sort of error that happens when you do an experiment. And again, especially for example, I think we were talking about a precipitation experiment. So if you sort of performed a precipitation reaction, you collected the precipitate on like filter paper or something like that, it usually is sort of wet because it comes from a solution that's been mixed together. And if you're impatient and stuff like that, and really don't let your precipitate dry, maybe you don't put it into a drying oven or something like that, and you just kind of rush and reweigh it. When you go to reweigh it, you're going to get obviously the mass of your precipitate that you collected, but you will also get some inflated mass numbers associated with the water that's still there. So again, a very common sort of experiment is that sort of collection of like a precipitate or something like that. And again, in the brush, sometimes people don't let it completely dry. So when you go put it on the balance to weigh it, you're envisioning what you're seeing is your solid, and the mass that you see is all your solid, but you're actually getting a lot of water weight with it. And what that would do is drive up your actual yield higher than it should be. And again, then you divide it out, you may actually end up with over 100% yield. Again, usually means that you made a mistake, and that would be a big mistake there in an experiment such as that. Now, getting back to sort of limiting reagents, as we talked about last time, first off, the way you sort of know that it is a limiting reagent problem versus sort of a regular stoichiometry problem is really based off of the information given to you. So when we're dealing with sort of a regular stoichiometry problem, really you're given one piece of information. And when I say one piece of information, enough information to really get to moles of somebody. And in that sort of situation, what we typically do is 4 basic steps of stoichiometry, which is balance the equation. Remember, nothing works correct if it's not balanced. We convert to moles. And again, we convert to moles using the molar mass from the periodic table. And that'll be grams per mole, right? Just the molar mass. We then do actually the stoichiometry part, which is go to the balanced equation and find that mole to mole relationship. And lastly here, we sometimes have to do number 4, which is convert from moles to some other units. And a lot of times here on the back end of the calculation, we have to use molar mass as well to go from, again, moles to grams. Remember, molar mass from the periodic table is really our conversion factor, right? To do those 2 conversions, go from grams to moles or moles back to grams. And in a regular stoichiometry problem, you know, you can roll through these 4 steps in order. If something's done for you, you just kind of skip ahead and go to the next step. And the way we know, though, that it is a limiting reagent problem, as we also talked about last time, is in a limiting reagent type problem, you're given enough information to get to moles of all your reactants. And I'll put all reactants. Usually we're dealing with 2. Could technically be 3, I suppose, but usually it's just 2. And you're able to really get to the moles of all your reactants. And that's definitely the key as to how you know it's a limiting reagent problem. So what is the difference between sort of a basic stoichiometry problem and a limiting reagent problem? The difference is at some point you need to figure out which one is the limiting reagent. There's a few different ways we talked about last time that you could do that. A very common way is to do 2 separate stoichiometry calculations, one starting with each reactant going to the product, 2 separate calculations, and whichever one produces the smallest amount of product is both your limiting reagent and your theoretical yield. Another very common approach to doing limiting reagent problems is to first do a stoichiometry problem between the 2 reactants and basically figure out that if you wanted to use up all of one of the reactants, how much of the other reactant do you need to toss in there? And you would do that calculation and then compare to how much you started with. And if you have enough, then that reactant is the excess reagent. If you figured out that you needed 5 grams of this reagent, but you're only starting with 2 grams, that would tell you that that reagent is a limiting reagent and you do not have enough. So those are 2 very common sort of approaches to doing limiting reagent problems. We talked about a third approach, which again, as I mentioned last time, sometimes can be, I don't want to say one's better than the other, but it can help you answer a lot of questions very quickly. And that's what we talked about, using ICE tables to do that. ICE tables basically means initial, change, and for us, end. And we represent the change when we go from, say, reactants to products with an X. And this would be minus X on this side, plus X on this side. Also really important is if the guys have coefficients. that you also include it in the change part. That's critical when we do an ice table because that takes care of all the mole to mole relationship. And again, if you don't do that, you're technically not doing the proper mole to mole relationship. You obviously would get the wrong answer. What we basically do in this sort of situation, I guess we would have multiple reactants here. What we do in this situation is basically set each of these guys equal to 0. And the smallest number, once we solve for x, is our limiting reagent. And the nice thing about that, as we sort of saw last time, is it's not only just sort of which one's our limiting reagent, but it gives us a very quick way to figure out how much of a second product we would produce if we had a second product. We also can figure out, which is a very common question, how much of your excess reagent is left over when the reaction is done. So, doing this method is a very kind of convenient way without necessarily having to backtrack to the very beginning and kind of do a separate calculation to answer all those questions. You kind of plug and chug it in and kind of really at that point go from moles to grams and very quickly sort of get all the answers that you would need. The added benefit, as I mentioned last time as well, is if you're taking 200B, it's pretty much like the calculation, very similar to this one, that you do for a good majority of that class. Any questions on stuff that we've been talking about last time here? All right, so I think we went through this TI example, so I think we are here. So why don't we take a few minutes here and let us determine what it's asking in this question. Let me see what it's asking. Move some stuff out of my way. We have 100 grams of ammonia is reacted with 100 grams of carbon dioxide, and we produce 120 grams of our product. We want to determine the percent yield. So take some minutes here and work through this. We can give you some information that might be helpful. Carbon is 12.01. Looks like oxygen is 16. Nitrogen is 1401. I think that might be all that you need. All right, so take a little bit of time here, see what you come up with. We're looking for what is the percent yield in this reaction. Let's take a look here and kind of see how we're doing. Let's talk about a couple of things, make sure everybody's on the same page. First off, this is a problem. Hopefully you got that. So here we have an equation. It is balanced. We're given 100 grams of ammonia, which is this guy. We're also told that it reacts with 100 grams of carbon dioxide. So right from that two pieces of information, we obviously have grams of NH3, we have grams of CO2. That allows us to get to the moles of each of these guys, and that should automatically tell you that this is a limiting reagent type problem. So because we have enough information to get to the moles of each of those, definitely going to be limiting reagent. We are producing 120 grams here of our product. So we're producing 120 grams of this guy. And we want the percent yield. So the percent yield is our actual divided by our theoretical times 100%. 120 grams is our actual yield. So we actually have the top part here. That means we do need to use stoichiometry here to figure out the theoretical yield from the calculation here that's happening. Any questions on that so far? All right, so we really do want to, no matter sort of what method you choose, and as we talked about last time, I don't necessarily have a preference. So again, if you prefer doing these limiting reagent problems a different way that you learned maybe before, I have absolutely no problem with you doing that. It's perfectly fine. But again, I'm going to probably take the ice table approach here, just kind of show you how to do it again. But what we want to do is really the same steps for any approach. First one is always want to make sure that we have a balanced equation. I see a 2, so I'm fairly confident that we got a balanced equation going on here. the next thing we really want to do is convert what they gave us into moles. So the first thing we would want to do is take the 100 grams of NH3, and we would want to convert that into moles. Here we would go to the periodic table. We have one nitrogen at 1401. We got 3 hydrogens at 1.008. That's going to give us a 1703 grams per mole. Grams are going to go on the bottom here so that they cancel. And that will again convert our grams into moles. And looks like we end up with, we'll call it 5.872 moles. And really the reason why we has to kind of get everybody into moles is the basis of stoichiometry is a mole-to-mole relationship. So in order for all the units to cancel correctly, we got to get everybody into moles. We then want to do the same thing for our CO2 here. Again, going to the periodic table, 1 carbon at 1201 and a couple of oxygens at 16 tells us that we are 4401 grams per mole for our CO2. Again, opposites cancel, so grams cancels, leaves us with moles. So 100 divided by 4401 gets us, we'll call it 2.272. Too many T's in this number. 2.272 moles of CO2. Any questions up to that point? Okay, so I'm going to now do my ice table approach here to help me answer this question. So really when you do it, you want to start with the equation. So I'm just going to rewrite the equation here. And remember, initially we're going to take those moles that we just calculated. So initially we got 5.872 moles of NH3. We got 2.272 moles of CO2. And as we talked about last time, it is very safe to assume that you are not starting with any products at this point. We then get to the change part, and remember the idea here is we're assuming that this reaction is heading in this direction, going from reactants to products, which means over time we would expect our reactants to decrease because it has to make products, and we would expect our products to increase. The way we represent that is with minuses and pluses. So on the reactant side, it would be minuses because it's decreasing. So minus 2x here. Again, the 2 really important for the stoichiometry part. This would be minus x because really the coefficient here is 1. Now we're coming to our product side. It would be plus x also because the coefficient is 1. And this would be plus x as well. Again, the coefficient here is 1. That then gets us to the end, and all we're going to simply do is just bring everybody down. I'm going to get rid of the moles part just so it doesn't get too messy in terms of numbers and stuff. Any questions on sort of how the ice table is set up here? Okay, at this point, what we want to do is simply set each of the reactants equal to 0. The idea there is we're going to see how much we can use up, basically. So if I set this equal to 0, we essentially get 5.872 is equal to 2x, which means x would equal 5.872 divided by 2, basically, 2936 moles. And again, remember, these are moles. We will also set this guy equal to 0, and that's pretty easy to figure out. X then equals 2.272 moles. In this particular case, we're looking in comparison of the 2 x values that we just got. So we're looking at this x value versus this x value. And the one we're looking for in our case is the one that is the smallest. And in comparison, this guy here is the smallest, which means that is the smallest, and that would mean this guy is going to be our limiting reagent. Also means that we don't necessarily need this part anymore. And we know just from that there that our CO2 in this reaction is our limiting reagent. And as we talked about last time, if you're able to determine one as either being limiting or excess, the other guy has to be the opposite. So that would mean that our NH3 here would be the excess reagent. Any questions on that? Now, here's really, again, where sort of that benefit comes into play. We now know that our X value here is 2.27 moles, and that X is this X. It's also this X. It's also this X, and it's also this X. So that X is pretty much every X that we see in that particular table. We'll start with what we're interested in, which is this guy. So looking at the table, we see that the moles of our product here based off of the table is equal to X. And now that we know what X is, we know that basically we have 2.272 moles of our product. So we want to figure out how many grams that is because our actual yield was in grams. So again, we would need to go to the periodic table and figure out the molar mass here of this guy. That's 2 nitrogens at 1401 plus 4 hydrogens at 1.008 plus a carbon at 1201 and an oxygen at 16. That gives us 60.06 grams per mole here. Moles are going to cancel. And if we multiply that by our 2.272, tells us we got about 136.5 grams of our product here would be produced. This is our theoretical yield. Any questions off of those steps there? So what is left to find? Well, we have now just found our theoretical yield. We had our actual yield in there. We are ready to really solve for the percent yield. So the percent yield in this case would be our actual, which was 120 grams, divided by our theoretical that we just calculated, which was 136.5 grams, times 100%. And if we do that, looks like maybe 87, 91%, not terrible, percent yield. Question on any of those steps? So as I mentioned before, again, just to kind of show you the benefit perhaps of doing it this way, we were not asked in this case, how much water would we have produced? But if we wanted to know how much water we produced, we simply could go to our table. And in this case, we see that the moles of water, because I don't have to put in parentheses, equals X, which means in this case, we would also produce 2.272 moles of water. Again, going to the periodic table and getting the molar mass of water, which is 18.02 grams per mole of water, we can, in a very quick period of time, figure out that in addition to 136 grams of the other product, we would also make 40.9 grams of water would be produced in this reaction as well. That would be the theoretical yield of water. We also could, if we wanted to, figure out how much of our excess reagent would be left over, which is, again, another very common question. Excess reagent in this problem would be NH3. So looking at our table, we see that the moles of NH3 equals 5.872 minus 2x, which means we would take 5.872 minus 2 times our x value of 2.272. And that would get us 5.872 minus 2 times 2.272. We would have basically 1.328 moles of NH3 left over, using the molar mass that we used at the beginning of the problem for NH3, which is 1703 grams per mole. We would have about 22.6 grams of NH3 left over. Here we started with 100 grams, so we used about 78 grams of NH3. So you can see very quickly you could really get to sort of every answer that you might ever be asked in a problem like this. That is correct. So if your question is when we want to find out basically how much products that we produce, it's always based on the limiting reagent, because kind of like the example there, you know, if you have two things to make the product, you're going to put those two things together to make a product. Once you lose one of those things, there's no chance that you would be able to ever make more product at that point. So it's always the limiting reagent that basically determines how much product you could actually make. So as soon as that runs out, it's gone. I think I used like a hot dog and hot dog bun example the other day. You know, if you run out of hot dog buns, you can't have nowhere to put your hot dog at that point, right? So it really limits sort of it, and it's always a limiting reagent. So the way that we do know that it was a limiting reagent problem, and this is usually always the case, it's really back where we started it here. So we come back to our original problem here. That what the question that was asked was, in it, what they told us was that we're starting with 100 grams of this guy and also 100 grams of this guy. And basically what that means is we do have enough information to basically get to the moles of each of our reactants. And that's really how you know it's a limiting reagent problem. If you're given enough information that you could take it, and by the way, it doesn't have to be grams of both of the reactants, but you know, whatever pieces of information you're given, if you're able to take that information about the reactants and basically convert it into moles for both of the reactants, then it definitely is a limiting reagent problem. If you sort of think about some of the kind of basic stoichiometry problems that we did before these, we were only really given one piece of information, a piece of information about maybe one reactant, a piece of information about one product or something like that. But whenever you're given enough information about the reactants, both reactants that are there, it's usually two reactants in most cases, and you have enough information really to convert to moles. That's the key. You have enough information given to you in the problem to convert to moles for each of the reactants, then it absolutely is a limiting reagent problem. Other questions on that? So again, hopefully you can see that, you know, there is maybe some benefit to doing this way. But again, if you did it using one of those other methods we talked about, you should hit the same numbers at the end as well. So again, you don't have to do it this way, but it is sort of I'll say an organized way that you could get to all the answers that you need fairly quickly. Question on stoichiometry, limiting reagents, how to do these problems. Obviously, you do need to be able to figure out all these things. What's the limiting reagent? What's the excess reagent? How much product you would produce? What's the percent yield? How much excess reagent would be left over? Any questions on any of that stuff there? Okay, then we are going to switch gears a little bit, and we're going to kind of move into talking a little bit about solutions, concentrations, Then we're going to get back into some stoichiometry type problems, but stoichiometry problems involving solutions. And they're kind of done the same way, slightly different approaches, but we do sort of do it a very similar way. So this, by the way, is sort of the other method that we talked about last time. So you can see it starts with this is the same problem we just did. You start with converting to moles. And in this method, what we did here with this calculation is if we wanted to use up all of the CO2 moles that we started with, how many moles of NH3 would we also have to put in there? And that's really what this calculation is that we're looking at here. And what we would do at this point is go, this is how many moles is needed of NH3. This is how many moles we started with, kind of your starting amount on each of these. And we could see here that we do have enough. We only need 4.5. We have 5.8 to start with. So because that's enough, that would tell you this is your excess reagent. This is your limiting reagent. And again, that's the exact same thing that we basically determined in our calculation we did in the ice table. Once you determine that, then you start again and basically just do a regular stoichiometry problem from that limiting reagent all the way to the product. And again, you can see here, we end up with the exact same number that we did before. And then obviously at this point, we would put it into our percent yield like we did, and you end up with the same answer. So again, both methods, 3 methods, they all end up in the same spot if you do it correctly. Again, it's just more of a personal preference, whichever way you like to do it. All right, then let us actually then talk about solutions and really, again, talk about sort of concentrations and sort of what's happening with those. So when we talk about a solution, we're really dealing with what is referred to as being aqueous. And that's really what that aqueous symbol that we use next to things represent. And again, a reminder that there is a difference between aqueous and liquid. A liquid is a pure liquid, like if you just had water by itself. A solution usually implies that you took something that's kind of solid and dissolved it in something like water. So if you took some sodium chloride that's solid and dissolved it in water that's a liquid, that would dissolve and make a sodium chloride solution that is aqueous. So again, that's the difference between basically those two things. And a solution is really made up of 2 parts. One part is the solute, and the solute is the smaller part of the solution. And it's usually the thing that you dissolve in the larger part of the solution, which is the solvent. So in my example here of the sodium chloride solution, the solid sodium chloride is what's being dissolved. That would be the solute. The water here would be our solvent in this case. Water is a very common solvent. It's used a lot because it is polar, as we talked about when we talked about bonding. And that allows it to interact really well with ionic compounds. Because it's polar, it has a negative side and a positive side. So when you put something like sodium chloride in water, basically the positive ion gets surrounded by the negative side of water, which is the oxygen. And the negative ion gets surrounded by the positive side of water, which is the hydrogen side, right, being polar. And that's really what happens, when we make a solution and we take something and it dissolves. Sometimes people have the misconception that, if I take some sodium chloride and I dissolve it in water, it's just disappeared, it's gone forever. It's changed into something, and it really hasn't. What's happened is a ton of water molecules basically go and surround all the ions. So it surrounds all the sodium, surrounds all the chlorides, and before you know it, they get kind of worked into basically the water network. And when you look at it, it looks like disappeared, it's gone. But it's really not gone, and you probably have experience with this if you ever taken salt water, which is kind of a common experiment sometimes done in labs, and you heat it up, right? When you heat it up, what happens is you evaporate off all these waters, right? That's the first thing that sort of happens. At that point, when you start evaporating off all the waters, there's nothing preventing these two ions from basically coming back together, and you can get your solid sodium chloride back. And that's why it's a physical change rather than any type of chemical change that's going on in this particular case. So a solute is the smaller part, a solvent is the larger part. The good news, if you ever really has to identify what the solute is in a solution, the good news is it is usually the name. So if you have a sodium chloride solution, the solute is sodium chloride, probably water is the solvent. If you have a sodium nitrate solution, sodium nitrate would be the solute. So usually the name of the solution is the solute's name. Now, when we think about solutions, which is sometimes an interesting sort of idea, we oftentimes think of solutions as sort of being in the liquid phase, if you will, right? Like a soft drink. And in the soft drink, water's the solvent, and then there's sugar, there's carbon dioxide, all the bubbles and all that good stuff. Other things, I suppose, in there as well. But, you know, a solution could be air. Air is made up mainly of nitrogen, is the biggest component of air, followed by oxygen, and then argon, methane, and other gases, depending on where you're breathing your air. And something that's solid as well could technically be considered a solution, although we sort of visualize solutions as sort of liquids, but technically they could be something else, because really a solution is just a homogeneous mixture. And a homogeneous mixture means that everything mixes and is the same throughout. Questions on that there? So what we're going to talk about now is some concentration units. And when we talk about solutions, concentration is a big sort of unit, our big topic that is used with solutions. And the most common sort of concentration unit that we come across is molarity. And molarity is capital M. And molarity is basically moles per liter. It's really moles of solute per liter of solution. You should think about molarity as almost like a formula, because we can rearrange it and solve for other things. If we want the liters would be the moles divided by the molarity. And if we want moles, it would be liters times molarity. Now, we were just talking about stoichiometry and the idea that, you know, really the first steps of stoichiometry is to convert things to moles. And how do you know if it's sort of a limiting reagent problem or not? And this is a very common way that we deal with stoichiometry problems involving solutions. They oftentimes don't give you grams, but they will give you the volume and they will give you the molarity. And from that, you're able to really calculate the moles. So another sort of alternative approach to a limiting reagent problem that involves two solutions is if you're given the molarity and volume of two different solutions, it actually would be a limiting reagent problem as well, because you can get the moles of both of those reagents. So again, that's a very common way that we could kind of get to moles in stoichiometry, especially using solutions, because when we talk about solutions, you know, we usually don't measure them in terms of mass. We think about volumes and that type of measurements. Any questions on that? Now, when we have something that is of a certain molarity, for example, if we had something that was 4.5 molar, which is what the big M stands for, sodium chloride. What does that mean? Well, first off, I highly recommend that if you're going to do any type of calculations involving molarity, that you get rid of the big M. And the reason for that is what that big M represents in this case is we would have 4.5 moles of sodium chloride in 1 liter of solution. The number always stays with the moles part, and it's always 1 liter. We could also use it like a conversion factor. We could flip it around, do a little dimensional analysis, and go 1 liter on top is 4.5 moles of sodium chloride. So sometimes it's good to use molarity like a conversion factor, sort of doing dimensional analysis and watching the units cancel out. Why do I say it's a really good idea to sort of get rid of the big M? Because I can't tell you how often I see people do calculations with the big M and they have absolutely no clue where the liters are or where the volume is or anything like that. So it's really good idea to get rid of the big M, convert it into moles per liter. That way you can visually see both units and know whether or not things sort of canceled out correctly or not. Any questions on that there? All right, so why don't we try one here? Why don't you try one? What is the mass in grams potassium iodide that's required to make 500 milliliters of a 2.8 molar solution of potassium iodide? Let me give you some numbers here. Potassium is 3910 from the periodic table. And iodide is 126, I think, 126.9 grams per mole. All right, take a couple minutes here and see what you come up with. Okay, so let's take a look. So obviously we're given molarity, we're given volume. So we're doing something with molarity here. So we should think about obviously the molarity formula. And that is, again, molarity is moles per liter here. So we do have the molarity given to us. We do have the volume given to us, not in milliliters, but we can convert it to liters. So if you are not sure where to go first, we don't have moles. So that probably would be a very good place to start. Rearranging that, the moles would equal liters times molarity. So we do need to do a conversion of our volume. So there is 500 milliliters. There's 1,000 milliliters in a liter, and that would get us 0.5 liters. We now have our volume in liters. We have our molarity. I, again, as I mentioned before, would kind of take the molarity here and get rid of the big M and convert it into really like a conversion factor and go moles per liter. Again, we could use it in this form if we needed to. We could flip it around and also use it in this form as well. So I'm going to do this problem here to figure out the moles of the Ki. Really going to kind of do it like a dimensional analysis problem where we can see the units canceling. So I'm going to, again, use my molarity here as a conversion factor. In this case, I do want the liters on the bottom and the moles up on top here. Liters will cancel. We're basically taking 0.5 times 2.8. Going to give us 1.4 moles of our Ki. Any questions on that calculation so far? Now we want grams though, so we do need to go one more step. So we're going to take 1.40 grams of Ki. Remember to go from moles to grams. That is the molar mass from the periodic table. In this case, we just got one of each of those guys. So we're going to take 3910, add it to 126.9, going to give us a molar mass for Ki of 166 grams per mole. Again, really using that as a conversion factor. We need the grams to cancel. So they'll go on the bottom. Moles. I'm sorry, I went the wrong way there. I went the wrong unit. Try that again. Take two. Helps to start with the right unit, I suppose. All right, these are actually moles of Ki. There we go. And now we would actually put the grams up on top there, 166 grams per mole of Ki. Again here, now that I got the right units going there, our moles are going to cancel. So 166 times 1.4 going to get us 232 grams of Ki. Any questions on those steps? So what does that number really represent? Well, that number represents basically what you should go to the shelf. You should grab out the potassium iodide and you should weigh out 232 grams of it. Maybe grab a very badly drawn volumetric flask here. That's 500 milliliters. And basically put your 232 grams in there. The rest should be some water that goes in. Fill it up to the line, which would represent 500 milliliters in this case. Give it a mixy, shaky, and maybe not so much shaky. And you will then have a solution that should have a concentration of 2.8 molar, and you should have 500 milliliters of it. Any questions on that? And again, it's a very common sort of calculation using volume and molarity to get to moles. We use it a lot in chemistry. All right, let's try one more here, I think. Hopefully they end up with the same answer. That's good. So again, here's sort of a picture of a fancy way. It looks just like my wonderful award-winning drawing I just did there. But basically, this is a volumetric flask. Volumetric means expensive. It also means it has one marking only on it. So if this was a volumetric flask, that would represent our volume for that particular flask. So for example, if this was the 500 milliliters we were just talking about, typically on volumetric, you go to 2 decimal places. So what you would want to do is what they did here, put a little bit of water in there or whatever the solvent is that they're pouring in, enough to get it solid to kind of dissolve, really continue to add water a little bit at a time until it all dissolves. And then you take it to the line, which would be where a meniscus would want to be. And that would represent, in this case, if this was again 500 milliliters, 500 milliliters of it. It's a very expensive piece of equipment, but very accurate type of equipment to use to make a solution, much better than trying to make it in a beaker, which would be a terrible sort of use of equipment there to make a solution. We're concerned with really solution concentrations because, as I mentioned before, most of the time when we're dealing with something that's obviously a solution, it's obviously liquid and stuff like that. So, we very rarely sort of take our solutions to like a balance to weigh it to get things like grams and stuff like that. So knowing the concentration like molarity and also knowing some volumes and stuff like that, it gives us a very convenient way to figure out, how many grams may be dissolved in there, do those type of calculations. In addition, when we talk about something like molarity in terms of its concentration, it gives us a reference point as to how concentrated a solution is or how strong it is, or maybe not how strong it is. So if you just think about it, if you have a very large molarity, what that means, in order to get a large number, you would need a large number up on top divided by a small number would give you a large number. So if you have a large molarity value on something, it's really concentrated. And what that means is you have a lot of your solute dissolved in that solvent. So for example, if you had something that was 18 molar hydrochloric acid, that is a very high concentration of that strong acid, as opposed to if you had 0.1 molar hydrochloric acid. That is what is referred to as being dilute, and this is a much smaller value of M. And what that would tell you, in order to get a smaller value, you need a larger bottom number than a top number, which means we don't have very much of the HCl dissolved in there. It's mostly water. So concentrations give us several different sort of pieces of information. It tells us, how strong the solution may be, how much of the solid is sort of dissolved in there, if you want to think about it that way, really how much of the solutes in there, or how weak of a solution it is, how dilute it is, and sort of the practical application of knowing the molarity or figuring out the molarity along with the volume can get us to back calculating, if you will, how many grams we use to make the solution, how many grams of solutes dissolved in there and stuff like that. So it's sort of a helpful sort of understanding of what's going on with that particular solution. Yeah, there is sort of a limit in terms of how high a molarity can be. And it has a little bit to do with sort of solubility as well. I think we talked about solubility in an earlier chapter, but there is sort of a limit at a given temperature of sort of how much you could get dissolved, say in water, for example. There's sort of a limit based on temperature and stuff as to how much you could get there. Obviously, if you played with temperature, if you played with other things, you could, in theory, get, as much concentration as you want in terms of a molar or concentration or molarity. But for example, hydrochloric acid, 18 molar is a super strongly concentrated acid, and kind of like the highest you usually will see. You don't usually see like 20 molar, 50 molar, 60 molar, or something like that. In theory, I guess if you kind of played with a lot of circumstances, you probably could get there. But under normal sort of circumstances, again, it is a solution, which means there is a limit based on temperature and what you are dissolving, for example, in it, as to how much you could actually get dissolved in so much volume of, say, water or something like that. So in that sense, there is sort of a limit in terms of how high you can be. And it does vary depending on, it's depending on sort of the solute that you're dissolving. So for example, 18 molar hydrochloric acid you could do, but if you did something like nitric acid, 16 molars is typically where you kind of see it top out at and stuff like that under normal sort of circumstances and stuff like that. So it is sort of dependent on what you're dissolving. Other questions on that? Okay, so why don't we take a look at one more example here, molarity here. Why don't we do this one? What is the molarity of a solution that is made by dissolving, let's go with 42.5 grams of calcium chloride and enough water to make 375 milliliters of solution. All right, so take a couple minutes to see what you come up with. Calcium, 4008 grams per mole on the periodic table there, and chlorine, 3545 grams per mole. Is molarity, so we think about molarity as moles per liter. And if we kind of go through it and sort of see what we got going on, we have 42.5 grams of calcium chloride in enough solution to make 375 milliliters of solution. So we do technically have the liters part. We do need to convert it, obviously, to liters. We are looking for the molarity. So again, another important aspect of where we should maybe start is we do need moles. So we can definitely get the moles from the grams of calcium chloride. So we would want to get the molar mass there. So we would have one more of these guys here. And if we add that up there, we got a calcium at 4008 and two 3545s there. Going to give us, we'll call it 111. Do that. Grams per mole is the molar mass of our calcium chloride, again from the periodic table. So we're going to take the grams of it and do a conversion. So 42.5 grams of calcium chloride. Again, we want the grams on the bottom so that they cancel, and actually want to use the molar mass would be good there, which is 111 grams per mole of calcium chloride. Grams are going to cancel. That's going to get us 42.5 divided by 111. We'll call it 0.3829. 0.3829 moles of calcium chloride. So now that we have the top here, we obviously need to do our conversion and convert our 375 milliliters into liters, divide by 1,000, or you can just move the decimal point, and that will give us 0.375 liters. So that's what we need to get our molarity. We're going to take our moles divided by our liters, and we end up with 0.3829 divided by 0.375, call it 1.02. Now, in this case, again, the units do not cancel, so you could leave it as moles per liter, if you like, or you can leave it as 1.02 big M. Either way is perfectly fine. Question on that step there, our molarity in general here. And again, molarity is probably the most common unit of concentration that is used a lot. Any questions on that there? Okay. So we were just speaking about sort of these larger concentration of solutions or a smaller concentration of solutions. And how do we go from a larger concentration or a bigger concentration to a smaller concentration? It is very common that we do a process which is known as dilution. And dilution is basically the procedure from taking a solution that is more concentrated. These guys are sometimes what are referred to as stock solutions. Stock solutions are usually more concentrated solutions. And basically what we do is essentially we only add solvent. So we add some solvent. A lot of times that solvent, again, is water. Not always, but a lot of times. And what we end up with is something that has a lower concentration, and it is what is referred to as a diluted, actually write the right word there, diluted solution. And it has a less concentration or less concentrated. So why does that happen when we add more solvent that the molarity goes down? We can actually see why that is when we look at the molarity equation. Again, the molarity is our moles of solute divided by liters of solution. So when we add more solvent here, like water, when we do a dilution, remember that the solution is made up of two things. It's made up of the solute plus the solvent, which means when we add more solvent like water, what we're essentially doing is increasing the amount of solvent, which means we're essentially increasing the bottom part of our molarity calculation, if you will, which means the bottom part gets larger, the molarity gets smaller. And again, by adding more solvent, we're increasing the volume of solution and it's bringing our molarity down. like everybody, I'm pretty sure, is probably at some point, got yourself a big gulp, went to the thirst oasis there at AM, PM, whatever it may be, got yourself a really nice drink there, non-alcoholic soda type thing with some ice. And, perhaps you drank it, you're on your way to class, you leave it in your car or wherever you went to. You went and stayed there for hours or whatever you're doing. You come back afterwards, all the ice is melted in your soda. You're thirsty, you drink it, you do. You go, how bad could it be? I was only sat there for a few hours. So you give it a drink and go, maybe I shouldn't have done that. But it definitely doesn't taste, obviously, as good as it did when you first got it, where the ice wasn't melted. It was more concentrated. It had more soda than water. Afterwards, when you left your soda there, right, all the ice melted. It now has probably more water than soda, and it really tastes watered down and stuff like that. So that's the idea here. In terms of a dilution, we're basically lowering the concentration by increasing the volume of solution. The important part, though, is the moles do not change. So the moles that we have in that solution to start with is the same number of moles that we have at the end of the sort of solution when it's all said and done. The only thing that changes is basically, again, the addition of that solvent and the volume of that solution. There actually is a dilution equation that is commonly used. That's one version of it. Most people do the M1V1 is equal to M2V2. M is molarity, V is volume. And in this case, this is usually the more concentrated solution. It doesn't have to be, but usually the first guys are the more concentrated. M2 is molarity and V2 is final volume, and that's the less concentrated. Now, a couple of things with this. First off, sometimes people will use a more generic version of this equation, which is C1V1 equals C2V2. And what does C represent? C represents just concentration. And although most people use the M1V1 equals M2V2 version of it because molarity is the most common unit of concentration, you don't necessarily have to use molarity in this equation. You could use some type of other unit of concentration, like percent mass to mass, percent mass to volume, percent volume to volume, which we'll talk about in a bit in this chapter. But you can actually use any type of concentration unit, but most people will kind of use the M1V1 equals M2V2. Also, when you use this equation specifically, the M1V1 equals M2V2, you do not have to convert your volume to liters. You can leave it in milliliters as long as they are both milliliters. You could use liters as well, but you can use milliliters. So you might be wondering, I thought you had to convert to liters to times by molarity. And the answer is yes, you do. If you are not doing a dilution. So if you're just doing kind of a standalone molarity calculation and you have molarity and you have the volume, it does need to be in liters for it to cancel correctly. If you're using the dilution equation like this, it will work out okay because technically, let's say you're solving for M2. M2 would be M1 V1 divided by V2, which means if I take molarity times milliliters divided by milliliters, the milliliters cancel, and you end up with molarity. So it will work out fine if you use milliliters in this equation. It will actually work out fine if you use liters in this equation. Same thing will happen. You'll have molarity times liters divided by liters. Liters cancel. You end up with molarity. It should be noted that, again, standalone calculations with molarity, you do need to take the liters times the molarity, which is moles per liter, in order to actually get moles. What happens when you actually stand alone and just multiply milliliters times molarity? Well, you actually don't get moles when you do that. Molarity, although we think about it as moles per liter, is also sometimes what is referred to as millimoles per milliliter. And what I mean by that is when you multiply milliliters times molarity, you're actually doing this calculation here. The milliliters cancel and you end up with not moles, but what are known as millimoles. And that's essentially what you're doing here, because then you're going to divide by milliliters, the millis cancel, and you're back to moles per liter. So a couple side notes on molarity and liters and molarity and milliliters. You can multiply molarity by both, by itself, but it really should be liters because you usually need moles. So if you take liters times molarity, you get moles. If you take milliliters times molarity, you get millimoles, which is not usually what you want. So just keep that in mind. Again, the dilution equation, you can, again, use milliliters in there. It'll be perfectly fine, or you can use liters. Question on that? Okay. So why don't we try one here to finish up on how would we prepare 60 milliliters of a 0.2 molar nitric acid solution from a stock solution of 4 molar nitric acid. So why don't you take a second here and think about what you would come up with. To the end here, let's take a look at this. So first off, we're doing a dilution. We're starting with nitric acid. Actually, we're starting with nitric acid over here, and we're ending with nitric acid. So just so everybody's clear on what's going on, we basically have a bottle of more concentrated nitric acid that's 4 molar sitting here on the shelf. And what we want to do is basically make a new bottle or beaker of nitric acid that has a concentration of 0.2 molar and a total volume of 60 milliliters. So basically what we want to figure out is how much should we take out of here and basically dump into here. And again, this is a dilution sort of problem. So we will use our M1 V1 equals M2 V2. Again, the ones are usually the more concentrated. So that would be our 4 molar. V1 we don't know because that's really what we're trying to find is like how much to take out. We do know what we want to end up with. We want to end up with a solution that has a concentration of 0.2 molar and a total volume of 60 milliliters. Again here, because I'm using the dilution equation, I can leave my volume in milliliters. If you want, you can convert it to liters, is perfectly fine. But because I left it in milliliters, I will end up with milliliters when I solve for V1. So V1 will equal, in this case, 0.2 molar times my 60 milliliters divided by my 4 milliliters. And again, this is why I'm going to end up with milliliters. The molarity will cancel. That's going to leave me milliliters as the only unit that's left. That gives me 0.2 times 60 divided by 4. That gives me 3 milliliters. So what does that 3 milliliters represent? It represents the 3 milliliters of this 4 molar solution I should take out from my more concentrated guy and put into here. 3 milliliters. My HNO3. My more concentrated. All right, so that's definitely how I would start to make the solution, but I need to finish this off. And what else should I add to this? Well, I should probably add some water, maybe some deionized water should go in. How much water should I add to it? Should I add 60 milliliters of water to this? And the answer would be no, because if I added 60 milliliters of water plus the 3 milliliters I already have in there, I would actually end up with a total volume of 63 milliliters, which is not why I would add, obviously, 60 milliliters of water. So how do I figure out how much water I need to add, which is a very common dilution type of question? Well, we know that the final volume is 60 milliliters. We already know that we added 3 milliliters. So usually the volume of water is V2, which is our final volume, minus V1, which is how much we took out. And in this case, that would be 60 milliliters minus our 3 milliliters. Tells me that I need to throw in there, in this case, about 57 milliliters of water. Any questions on that there? So I would add there 57 milliliters of water. My 57 milliliters of water plus my 3 milliliters of acid in this case gives me a grand total of 60 milliliters, which is exactly what I'm looking for. At this point, we would give it a good mix. And when we would be done, maybe it turned blue, I don't know. We would then have a solution that has a concentration of 0.2 molar, and we would have 60 milliliters of that solution. Question on that there, or dilution. That's a very common question that's asked in dilutions is how much water should you add? And again, usually it's a V2 minus V1 situation to figure that out. Any questions on that or anything else we talked about here today?
Yeah, I have a quick question. You said something about using the liters to mole conversion rate when you have a standalone problem. What did you mean by standalone?
I mean, non-dilution. So you're not using this equation. So you're not technically using this equation, the dilution equation. So like the one we did before where, we had, I think it was maybe the first one or something, we had 250 milliliters of a 0.55 molar solution. So in this case, if I wanted to get the moles, for example, this is the only two numbers I have. I have to convert that into liters for it to properly cancel out in terms of the units. And that will give me moles. If I didn't convert it to liters in that problem, I just did this move right here, what I actually would end up with is not moles, but millimoles. And you never usually want millimoles in most calculations that you do. So when it's, this is what I mean by standalone, we're not doing like a dilution problem. It's just you have a volume, you have a molarity, you're going to use them together to figure out moles. You don't want to do it this way because it usually will give you the wrong answer. You want to make sure you convert it to liters so that everything cancels out correctly and you end up with moles. So in that situation where volume, molarity, and your goal is to just to get the moles and not really a dilution equation using this formula here on the screen, that's when you definitely always want to make sure you convert it to liters. Here you have the option, and you have the option because it's really two of these calculations right here. It's one happening on this side, one happening on this side. So if you leave it in milliliters on both, it's okay because it's this formula. It will work out okay. It will work out correctly. But if you're not using this formula and it's just a problem like this, like you want to figure out how many moles or how many grams, you do have to convert it to liters. Otherwise, you'll be off by that factor probably of 1,000.
Thank you.
You're welcome. Other questions? Okay, we'll lay it up there.